yeah, so I am pretty much just a name in this context. I'm sort of here as kind of like an overexcited hobbyist, I would say. I'm very envious of, I guess, many of the people here who get to kind of do this stuff, 9 to 5 or round the clock, close to deadlines, whatever it is. But this is some research that I started doing a couple years ago, and have been kind of slowly developing when I can, but it's now at a point where, yeah, it's kind of exciting to present to people, and things like that. So my name tag says Harvard on it, which is fraudulent at this point, because while I started while at Harvard, I'm now unattached to any academic institution, though it pains me to say. So anyway, let's get started. Oh, and we thought this worked, but it doesn't. That's okay. Oh no, it does. Okay. So obviously, this is a pitch spelling algorithm. Deciding upon enharmonic variance in the context. I was very excited during the keynote address when Elaine Gould was talking about these kinds of like contextual enharmonic decisions, because then I suddenly thought, okay, I'm relevant to this conference. That's great. I mean, it was only about 2 minutes, but I was like, okay, fine. So that was a relief. So hopefully that starts answering this question. Let's see if this actually works. Okay, I'll just use this. I think I'm not really here to say that replacing human intelligence and kind of like contextual information, because of course like sometimes I'm not dealing with let's say Mozart scores of fully tonal music or something like that, where often there is kind of like a right answer. I'm sort of thinking about like the example that Elaine Gould gave, where it was kind of like, okay, we're trying to do something with this spelling that's helping the performers and so on. So it's kind of giving us a sensible default, and the idea is I want it to be kind of like interactive as an engraver or a composer or whatever. Faster workflows. I'm trying to like pick up on kind of what you guys are looking for. Another thing is, sometimes, when you have a transposing part and maybe you start off with something that looks right in the concert pitch or whatever, and then you transpose it and all of a sudden it looks horrible. Having something that can do that for you can be helpful, I think. Taking the Doric line, more time for music. I should do my due diligence here, just tell you a little bit about some, this isn't a new kind of a line of attack. There are a few, maybe I'm about 10 years out of date here, but I don't think there's been much done in this area. I think people kind of think it's a solved problem. Typically, most of the work that's been done has been focused on like large corpus comparisons. So basically, like you write a pitch spelling algorithm, you test it on all of Mozart's scores, and then you see how many you got right, essentially. So the assumption there obviously is that Mozart's right, which most of the time he probably is. The context is pretty clear. So I hesitate with those kinds of measures when we're talking about like something that's going to be useful for post-tonal context, because then it's like, what is the right answer? Maybe I am sort of circumventing the, at some point I need to do a big, large corpus kind of test and just see how we're doing. But generally what I've gone for is kind of a different approach, where we're not so focused on accuracy, which is that second criterion. So the other criteria that Herning has given for like a good pitch spelling algorithm are parsimony, which is like avoiding accidentals and especially avoiding double accidentals. Cognitive plausibility, which is kind of like does this reflect like how we think about spelling pitches in the wild? And then generalizability, which I don't think is quite as relevant for our discussion today. And then there are a lot of kind of like real-time algorithms that are like focused on real-time transcription, things like that. But again, we're dealing with engraving here, so that's not so much the focus. So what I'm kind of hoping my algorithm does is not do real-time pitch spelling. It's dealing with kind of like the score as a static network of pitches that we kind of already know. And all of the interplay between pitches, like on the intervals, they kind of have a pull on each other, and so we're kind of trying to spell the score all at once. And then just kind of various, like, I think convenience things and things that might be helpful in like making it interactive in software. And just to give a little bit of a shout out, my colleague James Bean and I will be doing a bit of a workshop next door at 12 where we've got kind of like a mock-up proof of concept, some kind of idea of how that interactivity might work in like a pitch spelling algorithm. So things like, how do you inject your own preferences? How do you kind of tweak that? How do you kind of learn? It's not like machine learning, but there's a kind of parallel with this like inverse problem that I'll talk about. So just to kind of, in terms of actually presenting the algorithm, I'm going to do a bit of background, talk about how we like model spell pitches, run through kind of the algorithm, the theoretical side of it, and then look at some of the ways it can be customized and also extended to like dealing with microtones. So the main object we use is the maximum flow from operations research. And basically, if you consider like S like a source and T as sink, and all of the arrows as like pipes that allow water to flow in one direction, the question is how much water can flow through this network. And so the answer is 2. And you can see that because all the water has to cross these 2 edges. And so that is also called the minimum cut. And there's a just to kind of gloss over some details, there's a principle in operations research that says that maximum flow, like the amount of water that can flow through this water network, is equal to this minimum cut, which is essentially the edges that can kind of separate the source from the sink. So another way to think about the minimum cut is kind of splitting the graph into 2 sets. One where they all have value 0 and one where they all have value 1, and we only kind of incur a cost for the edges that go across. Oh, hello. Okay. That go across the cut. So in this example, we're only getting charged for the edges with weight 1. Okay. This is kind of how I encode spellings. So I split everything into binary variables. So there's 2 per pitch. 0, 0 means the flattest spelling, 1, 1 means the sharpest spelling, and 0, 1 means the natural spelling. So you can kind of see from a few examples. Let's look at, for pitch class 11, the natural spelling I'm calling B natural. The sharpest is A double sharp, and the flattest is C flat. And then we kind of hook them all up in a flow network structure. So right here we have the sink, the source, and for each pitch class we have this kind of the first binary variable, which is indicated with a down arrow, and then the second one, which is indicated with an up arrow. And so we kind of put together a whole kind of flow network that also includes the kind of connection between. Okay.
There's no problem.
Yeah. Oh. What am I doing? Well, yeah. So then there are also connections between pitches. So you can think of if an up node is attached to another up node, that's saying that those 2 pitches kind of want to have the same natural or sharp state. So think about something like pitch class 1 and pitch class 6. So kind of like C sharp and F sharps like to hang out. D flats and G flats are happy together and so on. Then the flip of that is when kind of you don't want, you want a sharper spelling with a natural spelling. So for example, pitch class is 0 and 1. So like 0, you want it to be C natural when you have like 1 as a C sharp. So in that case, you flip the connections so that basically whenever C sharp is in the natural state, C sharp, then C natural is in, it would be like a B sharp, so that would be in its sharpest state. Anyway, so those are just some details on how we kind of connect everything. And then you can kind of think of like this connection between the score, you know, breaking things apart in terms of like, on the bottom left we can see like the pitch class and the spelling that it takes, and then on the bottom right we might have some flow network representation where after running the minimum cut algorithm we get some assignment of values and we translate that back through the encoding into the concrete pitch spellings. So now that gives rise to two problem variants, because if you remember in the first flow network slide, there's edge weights that get attached to each edge in the network, and I haven't really told you how we actually figure out what those weights should be, and that's where this kind of inverse problem comes into play. So basically, if I've got a spelled score, or if I've got a bunch of interval spelled chords, then I can use those to kind of figure out, oh, wow, really jumpy. Okay, I'm not capable of doing that right now. So I can kind of extract the weights from spelled pitches. So, you know, if I have, every time I have a C sharp in my intervals, then, you know, that means I have a natural spelling, so I have a 1 and a 0, and so then that gives rise to, okay, what are the edge weights that would have given rise to that outcome in the minimum cut. So it's kind of like flipping everything around so I can extract weights. It's kind of like a learning process in a sense. So that's one of the nice things is what we'll do in the workshop is we'll be like feeding in various spellings. Like, okay, I like to see like an F sharp major triad all together. And then from that, I can like extract behind the scenes, like what are the edge weights that give rise to that. And then next time I run the algorithm, it'll be like, oh, okay, let's have the minimum cut in such a place that we get an F sharp major triad. So it's a nice way of being able to supply your own kind of data and make the algorithm better. So this is kind of the procedure with the forward problem. So we collect a group of pitches. We inject kind of adjacency or proximity information, you know, which nodes or which pitches should have a pull on each other in the context of a score. Then we construct the flow network, and then we do our graph algorithms to find the minimum cut, and then we kind of read off what that means in terms of spelling using the encoding system. You can also add like phantom pitches that are kind of like, you know, just kind of generally tugging the center of mass of the whole pitch space, almost like a tonal center. You know, I could add like a B natural that's connected to everything, and then I'm likely to get a lot more sharps in my spelling, basically. And the inverse procedure is I collect groups of spelled pitches, construct network from the groups, run the inverse algorithm, which takes the zeros and ones and gives me back what the edge weights should be. And then, I'll probably skip over the clamping, it's already an information overload. Let's just kind of make that more concrete. So we've got some passage. First we separate out the different events, split up kind of segments. So I'm using this double bar line to say things on the right-hand side of the double bar line won't influence things on the left side in terms of spelling. And then, so basically anything within these blocks, they can be kind of connected, so they can be like adjacent nodes. And then, you know, maybe I'll have some scale factor for linearly adjacent pitches, and then ones that skip, and then vertical connections as well. And then I'll kind of put that all together and scale by the edge weights that I extracted from the inverse problem, and then I can run my algorithm and get some results. And then, you know, there's another thing that I've been thinking about as well, which is kind of you can scale everything so that we kind of scale the final intervals first, because you know, the more natural spelling is I'd say the one on the right. And then yeah, so extending to you know, one of the things about the algorithm is it should work with you know, with microtonal context. So I'm just taking these, I guess the Smoothwall library calls them gold accidentals. So, you know, these have little arrowheads. So let's say we have a rule that basically we want arrows to point the same way in a chord, just so that all the intervals make sense. Then we can achieve this by basically doubling the size of the flow network. And then so have kind of all the up spellings on one side, all the down spellings on the other side, and depending on where the minimum cut falls, that's the orientation of the arrows that we get. Yeah, don't worry if you don't. I'm realizing this is kind of like a lot of information and it's actually kind of hard to grasp. But yeah, I can point you to like a written description of some of these elements and also explain things further if anyone's interested. So yeah, so right now we have like a completed open source implementation in Swift. So that allows us to make iPad apps and things like that, which we'll do in the next room. Yeah, so next steps are hopefully deploying it in software. So, you know, the proof of concept kind of thing we'll be showing in the workshop, and then also, so James, my colleague, has an interesting project, it's called DNM, which is, it's a work in progress open source music notation system, which is pretty cool. So we're hoping to kind of connect up with that. And then we're also, as part of the DNM project, we're working on a music XML reader and writer. So I'm interested in Jacques' talk coming up as well. So, you know, those are kind of next steps that allow us to experiment more and kind of get more intuitions around the algorithm. So obviously I'm kind of in this world and I've been thinking about it for a long time, and I think I'm aware that it's sort of, there are a lot of kind of glazed expressions, and so it's not necessarily the easiest to explain, but my hope is that this will be something that, you know, professional users, you know, in an ideal world would be able to use and kind of understand and tweak to their own devices. So I'm hoping to find ways of improving people's intuitions about the algorithm and how it works, and so that's kind of one of the purposes of the workshop that will be happening at 12. Yeah, thanks.
Let me ask the first question. Your algorithm, what is the practical application of it? For example, I could imagine you have a score and you press the algorithm button and then you get suggestions which notes should have a different pitch, they should be enharmonically changed. Mm-hmm. Is this the right application?
Yeah, yeah.
Okay,
yeah.
So this is quite interesting for people who develop software, especially the graphical user interface to
that's the idea.
Switching pitches.
And yeah, so for example, there's nothing really in the, you know, I referenced some other algorithms. There isn't really anything that you know, deals with things like you know, different microtonal divisions per octave systems and stuff. So, you know, that was also something that I was kind of aiming to try to help users with. You know, if they've got a bunch of sharps and you know, quarter tone altered things in their score, there isn't like a lot of help for like, okay, well, how should I actually spell all of these?
Okay, thank you.
Does your algorithm deal with modulation? So, I mean, changing tonal centers which are not explicitly notated.
Yeah, so there isn't anything that is like explicitly used. So, for example, in the Chen, Elaine Chu algorithm, sorry, you know, there's something called a center of effect, which basically traces what the tonal center is. Everything with this algorithm is strictly done based on intervals. So in the sense that the intervals in a section where you've undergone a modulation will reflect the change in the tonal center. That should happen automatically. Because, you know, the preferred intervals will change as you modulate, basically. Yeah.
There's no explicit detection of tone centers.
No. But one thing, so for example, is, you know, I showed that slide where there was a double bar line, and you might want to kind of separate those two contexts. So that would be a way of kind of enforcing that, so you don't have any like modulation bleed, basically. Yeah.
So let me see if I get this. You go through the score, you figure your segmentation boundary, and then within that boundary, you figure out what the relationship with the notes are.
Mm-hmm.
And then you figure best fit accidentals throughout that stack
Yeah.
of intervals.
Sure. Yeah.
And so then, like this slide where you have the note on the bottom, it's affecting all of the notes above it, so you can understand that this is probably the D chord or whatever it is. And then everything around that gets fit into that.
Yeah.
idea.
Yeah. Yeah.
Does that sound right?
Yeah, but it's all done just purely on the intervals. So there's no like, okay, this is the root of the chord or something like that.
Okay.
So that's one thing I was trying to do, especially, you know, maybe, where you don't necessarily want to say there's one root, but you just want to focus on intervals. Maybe you're dealing with, you know, intonation issues in rehearsal, and you just want kind of all the intervals to be nice for the players or something like that.
Gotcha. And is there a provision for things like major thirds as a major third sounds really different than a minor third?
Yeah, so not, there isn't, so it basically assumes equal division per octave. Is that what you're referring to?
Yeah, in terms of intonation.
Yeah, so there isn't so much, so yeah, I'm kind of assuming it's like a piano keyboard.
Have you done any comparisons of your algorithm against Meredith or Chen, what have you, with, say, post-tonal music? How do they look?
That's like a next step, I think.
Yeah. It's really interesting to see that.
Thanks, yeah.
Thank you very much.